All right, AP Physics students, this is a look at the second of two kind of iconic electric circuits that you've been looking at this week. And because we had a snow day on Wednesday, we didn't get a chance to talk about this. So this is our way of kind of catching up here. It's in some ways a relatively simple circuit to think about, and something that you've sort of figured out already is the relationship that exists amongst the voltages and the currents. Okay, you've already discovered that if you take a voltmeter and put it here, you'll of course get the battery voltage, whatever that is, and if you place your voltmeter across R1, you'll get exactly the same voltage. And if you place it across R2, you'll get that battery voltage yet again. So that leads us to this statement right here, that the battery voltage is equal to V1, which is equal to V2. And the equivalent mechanical analogy is that, as we've talked about in class, if you're in the library, you actually have three different ways of moving from the library to the cafeteria, and in each particular case, you lose a certain amount of potential energy, whether you go through the middle of the building, or on the sort of art studio end of the building, or on the middle school social studies end of the building. You go from the third floor down to the bottom floor, and lose the same amount of potential energy every time. The current, however, I0, the original current or the supply current, comes to this junction right here, and then every individual charge either moves through R1 or moves through R2, delivering the potential energy that they picked up with the battery. But the charges either move through this path or through that path, and then at this point right here, let's see if we can get a at this point right here, the currents recombine to create I0 again. So that leads us to this statement here, that I0 splits, and this is indeed called a current splitter or a current dividing circuit, and the current splits into I1 and I2. So the sum of those two has to equal I0. If R1 and R2 are the same, then the currents are the same, but they're not necessarily the same. Here's a couple of pieces that we haven't looked at yet. So some new ideas for you, okay? Like we said in our voltage divider circuit, there's something called an equivalent resistance. Okay, so statement about equivalent resistance in this case, or the total resistance of the circuit, is a little bit more complicated. For a series connection in the voltage divider circuit, the equivalent resistance or the total resistance was just R1 plus R2. Here, it's the product of R1 and R2 divided by the sum of R1 and R2. And that seems unusual, and there's a way to prove that, and maybe given a little bit more time we will, but I just wanted you to have this information because it's really helpful to be able to take a circuit like this and redraw it so that you have a single resistor that replaces this network. In this case, that single resistor would be the product of the two resistors divided by the sum of the two resistors. A natural question then would be, given this circuit, how does the current split up? What proportion of I0 becomes I1 and what proportion becomes I2? The greater the resistance, the less the current will be, and so this turns out to be an inverse relationship. So you could write it like this, that I1 over I2 is equal to R2 over R1, which kind of captures the inverse relationship of this. If R2 is many, many, many times bigger than R1, then a lot less current would flow in as I2, and a lot more current would flow as I1. But let's pursue this a little bit further, okay? There are a number of reasons why this works out, but let's take a look at one in particular, okay? Let's cross multiply. and see what happens. So if you cross multiply, you're going to get I1 times R1 and I2 times R2, so that's what happens when you cross multiply. But notice, this is I times R for resistor number 1. According to Ohm's law, that's V1. And over here we have I times R for R2. And again, according to Ohm's law, that's V2. And so we have V1 is equal to V2, which we knew right from the top. We've discovered that earlier, right? But now, starting from this inverse relationship, cross-multiplying, and using Ohm's law, we come back to that same idea. So in fact, we could have gone the other way. We could have started from V1 equals V2, replaced those voltages with currents times resistors, and then rearranged to get currents on one side and resistors on the other. So this is the way the currents split, and it's all a product of the of Ohm's law. Okay, so that should help you a lot. What you're going to do now is take your Ohm's law video, take this current splitter video, and you're going to finish up the last two handouts that I gave you earlier in the week, and try to complete those for a habits of work grade for this week. Okay. Good luck with all that, and be helpful to one another. Have good, healthy, collaborative conversations. Particularly if you're stuck, don't stay stuck. Find somebody to talk to. Okay? Good luck.